Yassine Eben Aimine from Synopsys. He's an applications engineer, and he's going to talk about how to reach your target ISO26262 ASIL with a unified fault classification flow. Yassine is a veteran in the EDA industry with 20 years of service at Synopsys. He has worked on several parts of the IC design and verification flow, ranging from synthesis, ATG to verification. Yassine is currently Synopsys FUSA application expert for digital IPs and SOCs, and provides general technical guidance and support to Synopsys customers in the UK. Over to Yassine.
Thank you, Mike. Thank you, Sarah, for getting us to this stage. So I'm going to spend 20 minutes or so to talk at a high level of what the requirements are for ISO 26262 from a verification perspective. I'm going to touch a little bit about the Synopsys products that help you achieve your target ASIL using this unified fault classification flow that Synopsys has developed. I'm just trying to advance the presentation here. Okay, how do I? Okay, so the agenda that I've put together for today is to talk about the requirements for ISO 26262. I'm going to talk a little bit about the metrics that are required generate, and then I go into the detail of how you conduct processes such as FMEA and FMEDA and fault injection campaigns. And then I'll finish by giving you an overall overview of the Synopsys Unified Functional Safety Verification portfolio. Okay, so we always start with this infamous picture of a car involved in a crash to tell you how serious functional safety is in automotive products. So this particular case is a very well documented case of unintended self-acceleration back in 2010, 2011. So we're all familiar with electronics in automotive products, in cars in general. So for a long time they were there as a comfort feature, infotainment, things that switch on lights and so on. They're far more critical in terms of safety today because they take in many of the tasks that humans were taken to drive the particular car. So automatic braking systems are all developed as a safety feature, adaptive cruise control, automatic lane keeping, as well as the full-fledged autonomous driving experience. So these safety systems are great. But obviously they bring a lot of challenges with them because they're transferring the risks from the driver to the technical systems and to you guys here in the room, the designers of these systems. So safety is a fundamental requirement when you're designing an automotive system to guarantee a tolerable risk. And that's what the standard is there for, the ISO 26262. So I don't know how many of you, perhaps quite a few, have had the opportunity or perhaps the misfortune to look at the ISO 26262 document, several hundred pages. If you're dealing with hardware, chapter 5 is going to probably mean something to you. It's the part that deals with hardware, and essentially it's something that describes the requirements and general guidelines for designing an automotive system from concepts to the vehicle itself, vertically as well, from the vehicle level to the overall system down to the IP level, in which most of you are probably involved. So designing RTL, doing verification for IP that is going to go into an SoC, that's going to go into a tier 1 product that's eventually going to go into an OEM. And so functional safety deals with two major simple questions. What can go wrong in the car? And how do I minimize the impact or the risk if something goes wrong? That's really what functional safety is about. And that's something you deal with at the hardware level as well as the software level. And so the standard, the 26262, talks about the processes that should be followed to design these products. And it asks you in terms of requirement to generate work products, so specifications, documentations, verifications, reports, and so on. And as you'll see, it asks specific metrics to be generated, which can either be rated or can be measured as part of your verification flow. So drilling down a little bit about this functional safety, the standard says that the definition is it's the absence of unacceptable risk due to hazards caused by malfunctioning or unintended behavior or electrical and electronic systems. That's the overall definition, which obviously is broad, and we need to drill it down so that we can actually get to something quantitative. When you look at the type of failures that can occur according to the ISO26262, it talks about systematic failures as well as random hardware failures. And broadly speaking, systematic failures are caused during the design, during the development, perhaps during the manufacturing. That's because something has gone wrong in terms of either the specification or the way we've implemented that specification. Then you've got the random hardware failures, which will appear during the lifetime of the hardware element that's caused by some kind of a random defect or perhaps just through aging. So sources of these faults, the systematic faults, if you're an RTL designer, they are typically RTL bugs. So they have escaped our attentions as human beings. We have misinterpreted the spec. They can be prevented by doing a very good job in terms of functional verification. So by applying processes, design measures, design reviews, and using tools as well that check that your verification environment tests to its best ability for these systematic faults. Random hardware faults, they can occur unpredictably during the lifetime of a hardware element. So they can be detected and mitigated using some kind of a safety mechanism. And again, if you look at hardware, random hardware faults, there are two types. There's the permanent faults or hard errors. They're essentially always there. So they occur and stay there until you remove them or you replace the unit. And then you've got the transient faults or soft errors. And these are faults that can occur once and subsequently disappear. So bit flips, for example, due to some kind of a cosmic ray that's blasted the chip. And by the way, the example that I've shown on the first slide, the unintended acceleration was caused by a bit flip, which this manufacturer hasn't had a process for verifying. Okay, so how do we deal with these faults? Well, we want to go through a failure mode classification of a particular hardware element and classify what these types of faults are in that context. So you go through the hardware element, I don't know, CPU, for example, memory, and so on, and you say, hey, I want to list all of the failure modes of this particular element. First of all, is it a non-safety related hardware element, in which case all of the faults are safe faults. If it is not, then I want to be able to say, is this a safe fault, which means it does not affect the safety critical aspect of the functionality? Is it a fault that isn't going to be caught by any safety mechanism that I have in the design, and so on. This classification is a major step in doing it. And the output of this classification flow are two key metrics that the standard asks you to generate. That's the single SPF, the safety mechanism that leads to directly to the violation of a safety code, or a multiple fault whose presence is not detected by a safety mechanism or LF. So two key metrics that you're going to need to generate there. What sort of coverage should I have in terms of how resilient my system is? How many faults should I be able to detect, or how many residual faults should I have, should I tolerate in that particular design? So this is what your ASIL level would be. So how do you come to that conclusion? Why functional safety experts are going to have to look at three aspects of the application: the probability of exposure, so exposure to a particular effect occurring, or particular the controllability by the driver. So if something is, can actually the driver, an average Yassine like me, do something about it and stop harm occurring to themselves? And if the worst happens, what can the severity of the failure be? Okay. So using these three, you will determine a particular ASIL level, which goes from A to D, D being the most stringent. And so the metrics that you need to generate will have a certain criteria for these particular levels. So if you look at single point fault metrics for ASIL D, which is the most stringent, they want to demonstrate that you reach a minimum of 99%, which is obviously a very challenging figure to reach, which gives you about the effort it requires to go from simple functional digital verification to a functional safety verification. In other words, if you look at that, what it's saying that you want to have less than 1% of single points of failure detected in the device. Okay. There's the additional requirement, of course, for latent fault metric or multiple fault metrics. And in the case of ASIL D, it has to be over 90%. Okay. So these are the general requirements. What's the process for reaching a target ASIL level? And here we're giving an example of an ASIL D, which is the most stringent. Essentially, functional safety verification is used to evaluate that the target safety level is going to be achieved in the design. So if you go and calculate, whether you're estimating it or measuring it, calculate the SPFM and you find that it's below target, what you need to do is identify the areas of the design that's causing that and make changes to the chip design to address them. Okay, so calculate the metric, go through that diagram there. Is SPFM less than 99%? If it's yes, then you're going to need to analyze and add additional safety mechanism. How do you go about doing this? Well, there's two main processes. FMEDA, so that's failure mode effects and diagnostic analysis, and fault injection. Okay, so if I go into the detail of these a little bit, so that's the second part of my presentation. It was just to summarize the ISO26262 requirements from a hardware development aspect. So as I said, the first aspect, we need to be able to demonstrate and document that the design and the verification flows are robust. We don't want to end up with a systematic fault like that caricature picture there. When we go to manufacturing, we want to make sure that we ship a good product to the end application. So we use design for tests to minimize shipping escapes or defective products to the end application. And last, and this is probably the additional step that we need to do for automotive chips, is we need to demonstrate and document that safety mechanisms operate properly while the design is in operation, such that if a random fault occurs, we are able to mitigate the risk that it can cause. Okay. So let me now talk a little bit about FMEA and FMEDA and fault injection campaigns and how you go about those. But just before I talk about that, how do you ensure that our verification, functional verification process is robust enough such that it minimizes systematic faults? Okay, so obviously you do a lot of design reviews. You use the latest and greatest verification methodologies, constraint random, UVM, and so on. But there is more that you can do. What you can do is use design mutation, which is a form of fault injection, to check whether the verification environment can actually catch all of these possible faults, all of these possible mutations in the design. And Synopsys has had this product for a while, Certitude, which is a product that allows us to do functional qualification of your verification environment. So at a high level, what you're doing is you're trying to inject deliberately a bug in the design that models some form of an RTL bug. And you want to go and run, for example, if you're doing this for simulation, you want to check that audio regression is able to detect all of these possible bugs. You can repeat the same thing for formal verification for those parts of the design that use formal test benches. You can apply the same methodology for software. The product itself, so Certitude, has support for C, C++, and system C flows. It has support for RT level verification environments. So the design can be Verilog, it can be VHDL, and your test bench can be UVM, it can be a system Verilog. And that's something that will allow you to tick those boxes. These are part 8 and 9 in the ISO26262 document. Okay, so we have a methodology and we have a product that can help us demonstrate that our verification environment is robust. Let's now talk about how we demonstrate that our safety mechanism can actually deliver the job of catching faults as they occur in while the design operation. So the initial process is FMEA, so that's failure mode effect analysis. Essentially what this process allows you to do is you want to identify failure mode for the various blocks in the design, and you want to conduct some effects analysis. You're doing what it says, what can go wrong, essentially. That's what you're trying to capture initially. What can go wrong in the design? Start from some kind of a safety analysis document, create this FMEA. Now, typically people have done this in spreadsheets for many years. You can actually compute an estimated safety metric. So just using this FMEA and using information safety mechanism that you're going to be implementing. There are various safety mechanisms. Some of the common ones are displayed there on the screen. So dual core lock step. So if you've got a CPU, well, put 2 CPUs in there and make sure that they give the same answer. Okay. If you've got memory, you can have some ECC logic in there that checks it. CPU, you could have a software test library so that you're doing some kind of a self-test every now and then to check that the design is giving the correct answer and so on. Or you can have your own custom safety mechanism. But typically it's going to be based around the idea of redundancy, duplicating logic such that you have more than one answer and they all have to agree. If they don't agree that something has gone wrong, and you can use some voting mechanism to decide what to do. Is stop the device completely, or try again, or do something. So with this FMEA, you can compute an estimated safety metric. So that's the SPFM and LF that I've talked about earlier, but you can also measure it. Now, if you want to measure these metrics, you're going to need to run simulation. You're going to need to run a fault injection campaign to see whether the faults actually get detected. Okay. And as we'll see with the fault injection campaign, well, you can go again, you can go simulation way. So rerun the tests by injecting faults and see whether they get detected. You can run formal methodologies so that you can decide whether a fault is safe or not safe using formal technology. And finally, once you've done all of this, you get to generate an FMEA report and its manual, which are the requirements for certification. Once you get these documents, then you can pass them on to an assessor who you've been working with all along, and hopefully they're going to give you your ASIL A, B, C, or D certification. Okay, so as I said, FMEA and FMEDA have typically been captured in an Excel spreadsheet. Synopsys and EDA disrupted this functional safety flow. We're building products, so no more spreadsheets. I'd like you to think the same as me and agree that spreadsheets have always got limitations. They don't scale to very large designs, so large teams, they all have a format. People have to agree on that format. There's a number of entries. There's a lot of users that want to modify them. It's difficult to keep them under revision control, and so on. So we're going away from spreadsheets to high quality distributed FMEDA automation. So you can capture this in a software product, very much like you've been capturing transistors in schematics. This product is VC Functional Safety Manager. So as I said, it's something that automates user input. You can enter technology data to the node that you're using. You can perform architectural FMEA. You can enter design information. You can describe a little bit your safety mechanism. It's extensible, it's scalable. It's a client server type of application. Obviously, you can have as many clients as there are working on the particular project. As we'll see, there is a strong link to the fault injection campaign, and there is some automation there to bring that data into the tool. And the output is, well, you can export work products required for the standard. So FMEDA reports are generated automatically from this. It supports multiple report templates. Again, some of the common ones like SGS to UV is supported there. That's what it looks like. So once you've populated the data, you're going to end up with a dashboard like this, telling you, where you have been able to achieve the required SPFM and LFM. FMEDA and FMEA entry and automation. We've got several products that can help you estimate the ISO26262 metrics. One of them is a static analysis tool. So what you can do here is perform an early functional safety analysis so that you can understand design hotspots. Okay, so what's good about this is, well, it doesn't require any test bench. It doesn't require vectors. Okay, so it's going to go and analyze the design statically. So you can read either your RTL or gates. Most likely you're going to do the RTS stage because you want to do this early enough so that you can decide whether the safety mechanism is adequate enough for the ASIL targets that you're aiming for. And so instead of doing injection, what the tool is going to do, it does some probabilistic analysis of how easy it is to propagate zeros and ones from a flip-flop to the next flip-flop to the next flip-flop to a diagnostic point, a safety monitor, for example. So with this, you're able to estimate single point fault metrics. You're able to run functional safety analysis very quickly. So it's not trying to run a complete fault injection. So instead of spending 3 days doing a fault injection campaign on say an SOC, this is something that's going to return a metric within a couple of hours on a very large SOC because it's doing statistical analysis at this stage. It can be used in conjunction with fault injection later in the design cycle, but this is a tool that guides you towards designing a safety mechanism that's adequate enough for you. So the next you want to do is to start measuring the ISO26262 metrics. And yeah, an important aspect of doing that is classifying the fault. It's basically understanding some of the faults are going to be safe, so we don't have to worry about them. Others are going to be assumed dangerous. Others are going to be dangerous detected, and others are going to be dangerous undetected, and we certainly need to do something about them. Okay, so this is something that you can do, as I said, as part of a simulation process. Now, if you were to do this as part of a simulation process, and most likely you have to for things like ASIL-C and ASIL-D, bear in mind that you're dealing with a fairly large problem in terms of computation resources. So say you've got a 250K gate design, and you're looking at permanent faults, stuck at 1 and stuck at zeros, very, very easily, you're going to be looking at 500,000 faults, maybe up to 1 million faults. So, doing this by hand, going to a simulator like VCS and forcing a node to 0, forcing a node to 1, you're very quickly needing, a large infrastructure to do this. Zoix has a concurrent distributed parallel simulation technology to deal with this. So as I said, the naive approach would be, just run a simulation and inject the fault. You're going to end up with that. You're going to end up with a good machine compared to a fault machine and so on. What Zoix does, it says, okay, I am able to actually compute just the part that has diverged from the good machine. If I inject a fault, what's different? I'm only going to simulate the part that's different. With that, it can simulate over 1,000 faults in the same simulation. Yeah. And obviously, you can use modern compute grids to do that. So with that, you end up with this distributed simulation technology. And so it becomes viable to do fault injection as part of a simulation process. So you can get a turnaround time of less than 12 hours for a good, a block of P, 300,000 gates, 400,000 gates. We talked about how we want to measure the metric for ISO262. Zoix allows us to do that. It can actually generate diagnostic coverage, but obviously you want to feed that back into the FMEA and FMEDA process. That's something that we do automatically. So back annotation is automatically done using Zoix and VC Functional Safety Manager. And once you've done that, hopefully you got to a stage where you've achieved your numbers, and you can generate these FMEDA reports, which you give to your assessor. So to finish off with, very, very brief overview of the Synopsys products in this portfolio. There's more than just Zoix and VC Functional Safety Manager. We've made this announcement just recently. So this is a unified functional safety verification solution. We've got several partners that we've been working with to deliver this solution. And essentially what it allows us to do is have a unified platform. So I talked about unified FME and FMEDA. TestMac-Fuse is our static analysis tool. Certitude, many of you are nodding, they're familiar with the tool as a systematic failure tool. We've got several fault injection engines. So Zoix is the simulation one, there's a formal one, VC formal Fuse, and there's an analog one, TestMax custom fault. If you're going to run real software, you're probably going to need hardware acceleration. Yep, Zeebo is our hardware platform. And we've got a single debug analysis interface based around Verdi. All of this uses the same fault database, so that's FaultDB there. Okay. And this is our unified, this is the Synopsys Unified Functional Safety Verification Platform.